Thank you for coming out for today for the LMS Popular Lectures. I'm Kevin Houston. I'm the Education Secretary of the London Mathematical Society. Possibly some of you don't know what the London Mathematical Society is. Despite its name, it is actually a national society. We like to think ourselves as the Math Society of the United Kingdom. I know some people from the Institute of Maths and its Applications might disagree with that, but I think they're not here tonight. Is anybody here from IMA tonight? What? You're sort of. Oh, right. Yes, there's somebody, there's one person. Yes, they've got a talk on tonight as well. So, you know, you had a choice of places to go and you came here. Fantastic. Thank you. Oh, you didn't know about the other one? Okay, right. Right, so the LMS is a registered charity, and we give out grants to people to do research, to do things like work in pairs, or to go and visit somebody in a foreign country, or somebody come over here, run conferences and that sort of things. So in total, in the grants for this financial year, we've given out nearly £1 million in grants and other things, spent money of that sort of order. So you can see it's quite a large operation. If you're interested, then you can go online and look up and see what other things we do. We do other public lectures and things like that as well. Please go and have a look. And if you're not signed up, then there was a slide on earlier saying where to sign up. But I mean, I think it's fairly obvious, really. If you go online, look for popular lectures, there'll be somewhere where you can sign up, and then you'll get the information over the next for the next lot. Okay, so anyway, tonight we've got 2 lectures. We have 2 lectures in our popular lecture series. So first up, we've got Peter Higgins. So Peter is Professor of Maths at the University of Essex, and his search is in algebraic semigroups, which is the algebraic type that arises quite literally from the stringing together of words and compositions of functions. So, like most mathematicians, he tries to maintain a wider interest in things mathematical. So he's published numerous research articles. So many people don't know that mathematicians do actually do research and create new mathematics. Many people don't realize that mathematics does continue. They think, you know, at school they get taught about mathematics and they think, well, everything about maths is known, but that's not true. So Peter publishes research in mathematics and has written 9 books. He's also written 6 popular science books as well. So he will now present his lecture on my life in mathematics. Peter.
Well, thank you, Kevin. For the record, I'm a fellow of the IMA, but I'm also a member of the London Math Society. I'm very honoured to be here tonight, to be able to talk to you on their behalf. Now, how shall I begin? Well, mathematics is a subject that you need to meet on its own terms. You need to be able to follow things to a logical conclusion, and you need to maintain a kind of freewheeling state of mind. At least that's how it seems to me. From the time I was a small child, I used to try to think about maths without any reference to any applications, look it square in the eye, as it were. And I'm a pure mathematician, or as I sometimes say, I'm an openly pure mathematician. I actually study mathematics for its own sake and on its own terms. And tonight I'm going to talk to you a little bit about how I became a mathematician, and then, as time permits, something about the research I do. Now, my first genuine mathematical thought occurred when I was 6. I was in school, and my teacher, Miss Dite, she taught the class about multiplication, and she wrote this on the board, or something very like this, and she said, today we're going to learn about this symbol, the multiplication, or the times symbol. 3 times 4 means 4 added to itself 3 times. And you can't see that, can you? No. Now that's why I'm getting funny looks. Here we go. There we go. Miss Dite didn't have this problem. And so the answer is 12. And then the class was set some of these problems, repeated additions, and then problems using this multiplication notation. And she went around the class seeing how we were getting on. And the little boy behind me didn't understand, and he just added the two numbers instead of multiplying them. And she said very gently to him, "Now, no, Eddie, this is the new idea we're learning today." And I just thought immediately, that's not quite right, is it? It's not really a new idea. It's actually just a special case of addition. It's really an old idea that's been just dressed up a bit. And of course, I didn't say anything, and I may not have had the ability to voice my misgivings at that stage, but the thought had definitely taken root in my mind. And you might be thinking, he must have been a very pedantic little boy. He mentally fussing about this. Look, there wasn't a problem. Nonetheless, there is some merit to my thought, and it will come back again later in my talk, but bear that in mind. You should, by the way, be aware that children are very impressed by number prowess, because another memory I have was in first grade, and the teacher was doing something, and it led to 8 times 8. And she looked at us all, we were very small children, and she just said, "And I happen to know that 8 times 8 is 64. And you could have heard a pin drop. We were all aghast. How could this woman, who we didn't think was very bright, the kids are very judgmental, how could this woman just know the answer to that? It would take us hours to work that out, and we would still get it wrong. But somehow she just knew the answer without any effort in an instant. And she could see we were impressed, and she assured us that before we left primary school, we too would share this superpower that she has. She'd be able to tell you that 6 8s are 48, just like that. What? How would, yeah. So, now, I was impressed, and I went home that night, and I subtly tried to work into the conversation 8 times 8. And I managed, and I said it was 64. And I expected my family to be astonished at my obvious genius, and nobody batted an eyelid. As my parents and my older siblings, they were all in on the secret of 8 times 8. And I came to the conclusion that grown-ups aren't as stupid as they make themselves out to be at times. So, nevertheless, that was my second story. As for my third, well, you have to remember this is 1962, by the way, for your younger people in here. There's no calculators you could look at. There was no concept of a calculator. If you didn't know what 8 was, 8 times 8 were, you were pretty well stuck. You couldn't look it up in the back of the book. You couldn't ask the machine. So that's where we are. And we went on from there. At school, I liked maths, but still, I used to have trouble with something, subtraction. I didn't mean I had trouble doing subtractions, but it was a bit weird, because you were told subtraction meant takeaways. It meant it was the opposite of addition. But you could add any two numbers you like, but subtraction was always messier. For instance, you couldn't subtract 5 from 3. And this is explained as, well, if you have a pond and it's got 3 ducks on it, you can't take away 5 ducks, because you haven't got enough ducks. And I didn't say anything, but I really wasn't satisfied with this. I thought there must be a better explanation. How come we've ended up talking about ducks? That shouldn't be happening. There must be something more to this. And of course there was. When we went to secondary school, we learned about negative numbers. And now you could do any subtraction that came your way. So that was good, sort of. But still, well, with subtraction, you had to be really careful when there was brackets about. You never had to worry about that. With addition, there was something still mysterious about subtraction. And then one day, the teacher came in, and she demanded that we all believe that -1 times -1 was equal to +1. And for some of my classmates who were trying, perhaps not very hard, to understand this stuff, that was the last straw. That was obviously absurd. And how could that be? And there was no proper explanation forthcoming, except things like 2 negatives make a positive, which just sounded like an Orwellian political slogan. It did not sound like proper maths at all, Double think if we'd ever heard it. And this was the 60s, so, we're pretty never trust anyone over 30, we were told. We weren't having this. People were saying, and this is, for instance, one of the members in the class said, look, if I owe you £10, I owe this other person £20, I can't multiply them together and get £200, can I? And this sounded like a pretty convincing argument to us. And the teacher was taken slightly aback until she thought about it, and she said, yeah, that's true, but that's because your argument is rubbish. You can't multiply one pile of money by another pile of money. That's the problem. It's nothing to do with the way numbers behave, which is all fine. And in exasperation, she eventually just said, look, nothing else works, which just sounded desperate. It sounded as if, well, how would you put it? It just was resolved out of sheer frustration. You ended up doing this. So it wasn't entirely satisfactory. And we'll come back to that. The next episode of this kind, there was a few. I caused a bit of trouble at school. We learned trigonometry. And the same teacher, she's a lovely lady, she came in and drew a triangle on the board, a right-angle triangle, with an acute angle theta, and she labelled those two sides. And then she told us, we say the sine of the angle theta is the length of the opposite side, A, over the hypotenuse, C. And I wasn't having this at all. I was very confused by this. I said, that's the sine, okay, that's sine theta for the theta in that triangle, but what if you have another triangle, another right-angle triangle, with the same angle? How do you know you get the same value for sine theta? And she was a bit worried because she's worried about confusion in the class, and everybody was happy until I piped up and said this. And she said, no, it's fine, I'll explain that later. And I'm afraid I think I was a bit rude. I kept saying, basically, you can't go on until you've sorted that question out, otherwise it's all muddled. But it was the view of everybody else in the class, it would be better if I just shut up. But after class, she did actually come and speak to me, and she explained what was going on. She said, yes, you do need to say a little bit more to clarify this. And she did. She said, right, suppose you have another triangle. I'll draw it bigger. A right-angle triangle. Again, and let's say this angle there is theta. Now what's going on, of course, is that these triangles have two angles the same, and so they have three angles the same, because everybody knows the angles in a triangle add up to the same number. The number's actually 180 degrees. So that angle there is 90 minus theta, and so is this one. So these two triangles are forced to be similar. They're exactly the same except for a matter of scale. And that's what's going on. So if the scale factor was, say, k, that would mean this side will be k times a, and the hypotenuse will be k times c. When I go to calculate sine theta, using the rule she introduced, you'd get ka divided by kc, the k's will cancel out, and you do get the same answer. And I was quite satisfied with that, but insisted that she should have said that at the outset and it would have stopped any confusion. But she just smiled. She was prepared to put up with a little bit of insolence, I guess, on this point. And so this is an example of what algebraists and mathematicians call an idea being well-defined, by which it means initially the idea appeared to depend upon some arbitrary choice, but in the end it didn't. And this comes up a lot in higher algebra, and it even comes up in arithmetic. Whenever you put things over a common denominator, you start out with some fractions, but you change them for other fractions. That's cheating. No, it's okay, it'll all work out the same. It's the same underlying idea. And when students, I suppose we've got some maths students, we've got any university students here doing group theory and things like that. Well, it's all ahead of you. But when you do abstract algebra, using that notion in a more general situation is one of the challenges that students face. But it comes up all throughout mathematics. Now, just back to school again for a moment. So we started learning our algebra, and it's a bit like learning to walk. You get bumps and bruises along the way. And almost by experiment, you end up with a list. It's a very long, disorderly and unwritten list of things you can do and things you can't do when you're moving the symbols about. But at the same time, you get to appreciate the power of algebra, which stems not just from the brevity of the notation, but just from the universality of the symbols, and that allows you to do things you can't possibly do by words alone. For example, here's one of the things you learn somewhere in school. If you have two positive numbers, a and b, the square root of the product is the product of the square roots. And so, for instance, if you have a little exercise which tells you to simplify the square root of 45, you factorize it and say 45 is 9 times 5, and I can use this rule to write that as the square root of 9 times the square root of 5. That square root is exactly 3, so you get 3 root 5. And if you do that, your teacher congratulates you and says, good boy or good girl, you're using these ideas in just the right way. And if you're then very confident and you try to do something clever in a slightly different way, you say, oh, maybe I'll try this. 45 is, after all, 9 plus 36. And so maybe I'll just write that as the square root of 9 plus the square root of 36, which is, look, 3 plus 6, which equals 9. And the same teacher may go apoplectic upon seeing that. What? You're telling me the square root of 45 is 9. You're telling me 9 squared is 45, are you? Are you really? No, no, with a capital no. You wonder why people are scared of maths teachers, but no, how could you think? No. So what's wrong? Well, what works for multiplication doesn't work for addition in this instance. And as a teacher will no doubt say, the square root of a plus b is not equal to the sum of the square roots. And so you have another pair of do's and don'ts in your algebraic list. And you learn, you can do that, but never do that again, because I'll be in real trouble. And it goes on like this, and until you get to like GCSE level, O level, as it was in those days. When I was 16, though, we had a new teacher, a man called Mr. Wiseman. Came all the way from Baltimore to teach us the laws of algebra. I was in a little tiny country town in the middle of Australia, and he'd come all this way. I didn't think anything of it at the time, but it was quite fortuitous. And he started trying to explain to us that all the things we'd learnt about putting things over a common denominator, collecting like terms, even the mysterious, well, it's not there now, -1 times -1 equals 1, these could all be explained using a few very simple laws of algebra about the behavior of numbers, which themselves were very familiar. And I'll just write them up. The first one is what's called the commutative law. I won't write the words up, but I'll write the rule. A plus b equals b plus a. And if you have to add 3 or more numbers together, then you can only do them 2 at a time. But you have what's called the associative law that saves you in that a plus b plus c is the same as a plus b plus c. You know, for example, there is something going on here. Say 9 plus 3 plus 5 is 9 plus, 8, which equals 17. You bracket it the other way, you end up doing a different sum. 9 plus 3 is 12, but you do get the same answer. The associative law assures you that numbers will always behave this way. So we have the commutative law, the associative law, and these work for multiplication as well, but not for subtraction and not for division. You can soon convince yourself of that. For example, 8 minus 5 minus 3. Do the thing in brackets first. That's 3 minus 3, which is 0. If you bracket it the other way, 8 minus 5 minus 3, we get a different answer. 8 minus 2, which is 6. You don't get the same answer. So subtraction isn't associative, but addition and multiplication are. And there's one more. There's one more key rule, and that's called the distributive law. And it's important because it's the one rule which ties addition and multiplication together. And again, it's not very mysterious. I'll call it number 3. A into b plus c equals AB plus AC. When dealing in symbols, we normally don't bother writing the multiplication symbols in explicitly. It looks very messy. So this, for instance, is shorthand for A multiplied by B, A multiplied by C. From my pointer, going from left to right, we call this multiplying out the brackets. Going from right to left, this is called taking out the common factor, in this case of A. And given those laws, you can explain everything, all those rules. For example, putting fractions over common denominators. That's not a special rule, because dividing by C just means multiplying by the reciprocal, 1 over C. So this is what you're talking about, 1 over C times A plus B. And by the distributive law, you can multiply it by out the brackets and get 1 over C times A, which is A over C, plus 1 over C times B, which is B over C. So it's just a special case of the distributive law. It's not another thing you have to know, in a way. Another more substantial example is that A times 0, where A is any number, is 0. And that's a consequence of these laws. Why is that? Well, it's because A times 0 is A times 0 added to itself is still 0, so it's equal to that. Now we can multiply out the brackets and see what we get. We get A times 0 plus A times 0. And I'll just give it a name for the moment. I'll call that B. We all know it's going to be 0 in a moment, but let's call it B for the moment. And you see we've got a little equation, B equals B plus B. If I subtract B from both sides, I'm left with 0 on the left, just 1B on the right. Remember what B was. It's A times 0. So we've proved that A times 0 is 0. It's a consequence of the distributive law. It's not something that just has to be assumed. It's true. You've always known it's true, but it's a consequence of the distributive law. Well, if you're very astute, you might realize there's a little step between the second last line and the first, which involves adding the opposite of B. And if you go through it formally, you actually need to re-bracket that, and it uses the associative law. So actually you need the associative law as well as the distributive law to prove that A times 0 is 0, but it is. And once you've got that, you can go further. Even the mysterious minus 1 times minus 1 equals 1, the thing that caused the ruckus in class several years before, that's a consequence now of this fact here. I won't go through all the details, but you start with the fact that minus 1 multiplied by minus 1 plus 1, what's that? Well, minus 1 plus 1 is 0, so that's minus 1 times 0. And we've just proved that when you multiply any number by 0, you get 0. So we've got that statement. And now, if you multiply out the brackets here and follow where it leads, you'll find it leads to here. And that's what my teacher meant when she said nothing else works. That's all the explanation she gave. But what she really meant is, if we start off with those 3 really basic laws, this turns out to be a fact that cannot be avoided. And we don't have to start talking about Orwellian political slogans. It really is the way it is. So this is what Mr. Wiseman was teaching us. I would like to say a little bit more about this. You shouldn't confuse laws of algebra and results based on it with conventions. And here's an example. Sometimes people on Facebook put puzzles based on things like that. What does that equal? And you're supposed to say, multiplication takes precedence over addition, so that is in fact 3 plus 20, and the answer is 23. And that's correct. And the thing I want to say is that that's not a law. That is just a convention, because written in that way, without saying any more, it's ambiguous. And the convention is that when we write that down, we really mean this. We mean do the multiplication first, and so you do it, and that's what you get. You get the answer. If you want the addition done first, which is perfectly legal. You have to say so by putting in brackets to tell everybody to do the addition first, and then you do that and you'll get a different answer, and that's fine too. But it's a man-made law. We could do without it, but if we did try to do without it, we couldn't write this down. We'd have to write either this or that to tell people what we were talking about. So that's the way it is. But it does go back to that thought I had when I was 6, when Miss Diet started to talk about multiplication, when I said it's really the same thing. That justifies this idea a little bit, because when we write 4 times 5, as Miss Diet said, that means 5 added to itself 4 times. And so we can't really do this first addition until we've done that. And that's why the convention is the way it is. So my little thought wasn't entirely unconnected with what mathematics is really like. So that's how I like to justify myself in that regard. Anyway, this is what Mr. Wiseman was trying to teach us, and it wasn't going down very well. Most of the class were really quite worried, because we were about 16. We were pretty good at maths. We'd learnt a lot of maths. We had learned complicated things like trigonometry, log division, logarithms. Yes, we used to use tables of logarithms. This is a long time ago, because logarithms turn multiplications and divisions into additions and subtractions, and so they give you a way of doing that. And we were quite adept with that kind of thing. And in fact, I've got a slide, which is a little bit obtuse, but I did want to show it to you. Where am I? Now, don't press laptop, press PC. I was told by Tom. Go to the next slide. Does anybody here know who this gentleman is? Anybody? Hey, oh, yeah, Sam Cooke. He's not a plant, by the way. He's an expert on the Beatles, as I found out backstage. Sam Cooke. Okay, you don't answer this one. Does anybody know what that thing is? Yeah, okay, oh, good. Yeah, you see what your math types. Yes, it's now, for an extra, do you know what's coming?
Yeah, I think so.
Because I didn't think anybody would answer this. Does anybody know the connection?
Yeah, it says in a song, don't know much about science books, something like that. It's something to
It's the lyrics from Wonderful World, where Sam Cooke sings, how does it go? Don't know much about geography, don't know much trigonometry, don't know much about algebra, don't know what a slide rule is for. Yes, he confessed that. So this would be completely lost on youngsters nowadays. But at the time, that was a big confession, because everybody knew what a slide rule was for. It's a sliding logarithm rule, which helps you do the additions and subtractions of logs. Anyway, I just thought I'd work that in. For your benefit, as it turns out, Kevin. What do I need to go back to here now, don't I? Yes. So, nonetheless, I did appreciate what he was trying to do, at least I thought I did. The idea was to radically simplify algebra by clearing the decks and showing that we only need a handful of fundamental rules, or we can do everything. I thought that was obviously a good thing. But one of the things I wasn't sure about was the associative law. I'll just go back to my previous page, because you've forgotten which one's which, I imagine. Here we go. I was a bit worried about this one. And I asked him, since this seems to be saying something about adding numbers up in a different order, is rule number 2 really just a consequence of rule number 1? And he said to me, no, it's not. They are independent of one another, and there's no connection at all. And there are algebras which satisfy one of these rules and not the other. So he's right. They are genuinely independent. For example, does anybody here do matrices? Right, so you know, like matrix multiplication satisfies the associative law. You don't have to worry about brackets, but A times B is not equal to B times A. So that shows that, for instance, you can't deduce law 1 from law 2, because we have examples where law 2 holds. It's for multiplication, I know, but for a valid operation, that doesn't apply law 1. Anyway, I wasn't entirely convinced, especially as to his casual remark about there being no connection at all between the laws. And I came back the next day having had a bit of thought, and I said to him, what you said yesterday was wrong, or at least it wasn't quite right. And I showed him what I meant, and I was with some trepidation, but I said, look, what if you have commutativity, a plus b equals b plus a, and look at the case where c and a in the second law are the same. So I'll just write the laws up again. There's just these two. So we're assuming this one is fine, but the second one I'm not assuming is true. And I'm going to try and prove the second one from the first one. Now, I can't quite do it, but suppose that c and a are the same. And so start with the left-hand side there. Now, by the first law, I can write b plus a as a plus b. So I do that. And by the first law again, I need my little pointer here. I can swap the order in that addition and write the a plus b first, because I'm allowed to do that. And hey presto, I've managed to re-bracket it, just using the first law. So that shows associativity is true, at least in this special case. So what I've done is shown that in the presence of law 1, you can get a weak form of law 2. And I was a bit worried about this, because I thought he might tell me off for saying he was wrong or tell me there was just nothing in there. But he was really impressed. And I thought he's impressed rather too much, really. Because I said to him, this is really simple. And he agreed with me it was simple enough, and that there's probably nothing new in it, even though it hadn't occurred to him before. But what he said to me is, what you're doing is thinking about this exactly the way a mathematician would, and that you should seriously think about becoming a mathematician, because I had no intention of doing that at the time. I wanted to be a writer or a pop star or anything, but I wasn't thinking about that. And I didn't think about it too much more at the time. That was 1972. But by 1983, it had happened. I finished my PhD, and a lot of other stuff had happened. I'd gone from Australia to England. I got married. I had 2 children. I got back again, and yeah, I've forgotten a lot of it. But I did become a mathematician. So it's thanks to Mr. Wiseman somewhat. Now, how am I going for time? Yeah. I think I'll skip a lot of the boring. I had sort of more of a sermon about the way you should think about maths, and I'm probably going to leave most of that stuff. We did start slightly late, yes. Oh, well, I'll take that as an invite. Just going back to here, I mean, maths is hard enough to follow when it's written correctly, but when it's not, it can be practically impossible. And, where are we? Where did I write my... I can write it again, but... Yeah, my -1 times -1 is 1. You notice I put brackets around the -1. It looks very cluttered. Why did I have to do that? It's because I didn't want a clash of these symbols here, the minus and the multiplication together. And the reason why that's happened is because we've loaded the minus sign with 2 slightly different meanings. Because there it means the number -1, but of course it can also mean subtraction, which involves 2 numbers. And when you do this, mathematicians saying it's an abuse of notation or it's overloading a symbol. When you have a symbol that means 2 slightly different things. Now, depending on context, now sometimes it's fine because in a particular context it's clear what the symbol means. And so that's how we get away with it. But generally speaking, using one symbol to mean 2 different things can cause no end of confusion to everybody, mathematicians, students, and all that try to do mathematics. The other side of the coin is not having a symbol at all. When you're conducting a mathematical argument, do try to avoid the word it, the pronoun it. Give it a symbol and say what it means. If you do use it, it's not illegal, but make sure both you and the reader know exactly what it is. And if you use it, you should be able to stop yourself. If somebody asks you, what's it? You should be able to give an answer straight away. And thirdly, is that if you start talking about a symbol, an x or an n or a theta, make sure you tell everybody up front what the x and the n and the theta actually stand for. So, I say this kind of thing all the time to my students. And And they don't listen, so I don't know why you should. There was something else in that regard. Oh, yes. Sometimes I do write books, and sometimes other mathematical authors say, we write awful books. How do you write good books? And one of the things I tell them to avoid is the verb to be when discussing mathematics. And this is a slightly more subtle one. There's no law against it. But an example is, for instance, if you say the cat is black. Now, the cat is, it's nonsense really, isn't it? The cat is an animal, and black is a kind of colour, and animals are not colours. So why are you saying that? That is drivel. What you mean, of course, is the cat has black fur. And because everybody knows about cats, saying the cat is black is fine. But doing maths, you should never write down something like the cat is black, which is actually a false statement. That even though you think you know what you mean, the reader has the right to believe that what you've written down is exactly what you mean to say. And in maths, that's actually more important than perhaps in other fields. And bearing that in mind does help people write more clearly, even if you're writing in a fairly light fashion. Anyway, I don't want to give the impression that mathematicians, or give the wrong impression of mathematicians. We're going to be followed by another talk, which will straighten you out on this. But mathematicians do like to try to solve problems, use maths to solve problems, and they're generally on the lookout for maths you can do something with. But nonetheless, you are trying to prove new facts, new theorems as they're called. Right? Is every prime number, every number the sum of even number, the sum of two primes? Nobody knows. And if you're studying a question like that, your hope is that you'll find something interesting in that you'll be able to, how do I put it? Well, perhaps find a new way of calculating something, or perhaps just make a connection between one part of maths or another. You can't be too prescriptive in this regard because you are doing research, and research is about the unknown, and so you don't know what's going to happen. But that should be borne in mind. You're trying to do something which is genuinely worthwhile. We also shouldn't try to make a false distinction between pure and applied mathematics. For instance, a problem may come up in physics, and the mathematical problem may take on a life of its own afterwards and be of interest to other people that have got no interest in the original physics. And on the other side, you can have a piece of pure mathematics which doesn't develop any applications for decades or maybe even centuries. And the examples are everywhere. For example, in cryptography, computer cryptography, that's what keeps your data secret on the net. It's the basis of virtual currencies and so forth. The underlying maths is the maths simply of remainders when you divide. Sounds very prosaic. And in modern form, it was developed in the 18th century. But now well, everybody knows how important it is. Another example is Google. In 1998, the Google search engine blew all the others away. And it's not because they had better computers, it's because they had better mathematicians. They developed algorithms that use completely standard mathematics in networks and linear algebra. For example, one of the ingredients is what's called the Perron-Frobenius theorem for positive matrices. It was proved in 1907, and it's the basis of the Google search engine and of a host of other applications as well. But when it was first proved, it was just done as a piece of mathematics, which is obviously interesting and turned out to be important the best part of a century later in a very dramatic fashion. I'm going to talk now a little bit about what I actually do for a living. If I go back to the slides. Yes, I'll just leave the slide up for a moment. You can come across things almost by accident, by luck. In 2006, the Sudoku craze was just taking root, and I happened to notice that some little ideas I had involving networks could be used to construct a circular version of the puzzle. So I did that, and I soon got it, because the outlets were just crazy for anything to do with Sudoku. I soon got it put into, well, the Times, you can see there, and all the major newspapers around, Sunday Telegraph, and I forget what else. That's another another version of it in one of the papers, I'm not sure which one, Times, I think. That might have been the Telegraph. And by Christmas 2006, an American company had taken my idea. My youngest daughter and I wrote a book with these puzzles in it, and it was published in the States. And so an American company latched onto it, and they produced a toy for Christmas based on Circular Sudoku, and gave no acknowledgement to me or my university, I might add. But they did send me, after a lot of argument, they did send me actually one of the toys. And I think I've got a slide of it as well. And I really do treasure it because it was quite a strange feeling to pick this up, because I knew that the idea for it was in my head almost exactly 12 months earlier, and I was trying to figure out how to get it to work. And then a year later, it was really as a solid object in my hand, and that had nothing to do with actually producing. So I'm not angry with them. It's quite a novelty. And if you Google Circular Sudoku, you'll find like millions of hits. And I found even, I can put it on here. It's even turned up on the side of a sandwich wrapper. I have to make sure I don't press the wrong button. Here he is there. There we go. Somebody did. So that's quite sweet. So there we go. Is that what you really do? No. Most of the maths I do is quite esoteric, I'll have to admit, so I'm not going to be talking about it tonight. But to make up for it, I do try to write books occasionally as a thank you to the society I get to live in, I suppose. And they're normally about maths, and they normally do maths too, and don't just talk about it. But nonetheless, it's nice to get them recognised occasionally. And, whoops, oh no, don't press that, press this. I've done it now. Tom will tell me off. Oh no. PC. Oh, here we go. There we go. In 2013, I won the prize for the best Italian book about maths as a translation for the year before. And I'm very proud of this because it's been won by much more eminent mathematicians than me, including Cedric Villani, and in fact 2 French Fields medalists have won this prize. One before me and one after. Cedric Villani is, I think, in 2016. And I was going to say a little bit about that, but one thing I did want to mention, because it doesn't irk me, but in this version of it here, because this was written in 2007, I did make some comments about how unstable the international financial network looked. So if anybody ever tells you nobody saw the 2008 crisis coming, it's in there, and a lot of other places. It just wasn't heeded. I mean, it was really obvious to most people who thought about it that this wasn't going to go on for much longer, and that's the way it turned out. But we're still all here tonight, so that's a good thing. How are we going? Yeah, it's okay. Sort of lost sort of my place, but I've got about 10 minutes, haven't I? 5 minutes, something like that. I'll continue to. Oh yes, a more substantial topic. Burrows-Wheeler transforms. What are they? There's something I came across, and they're really quite magical. What a Burrows-Wheeler transform does is take a message and codes it in such a way that it can be compacted, compressed very easily, which makes it easy and cheap to transmit the data. And the way it does it is quite amazing. It's not a cipher, it's not a secret code. A cipher is a code where you, if an unauthorized interceptor gets hold of it, they can't get the message out no matter how hard they try. Burrows-Wheeler is quite the opposite. The idea it's easy to get the message out. Its purpose is that it allows you to compress the data. What is surprising is all it does is take the original string and permutes it. So what it sends is really a string of the same length, and the letter frequencies are exactly the same. So how can it be that the permuted version is somehow easier to collapse? It doesn't sound right. And it comes about, it's probably best if I now give an example. Say if the message you want to send is banana, the way the code is created is to take the message and to cycle it round write it, in this case, 6 times, because it's got 6 symbols in it. And you take your word and you start reading it cyclically. So we'd start here and write down A-N, A-N, A-B, which appears up here. And we'd take that word and we'd put that down the end, and we get N-A-B, A-N-A, which is down here. And so you get 6 words, and then you write them in dictionary order, and then you take the final column, and that's what you send. And why would you bother doing that? Well, do notice that the final column has lots of repeated letters in there. And that's not a fluke, because imagine you have an ordinary message that has, for instance, the word the in it 100 times. When you do the Burrows-Wheeler transform, what's actually going to happen? Well, there's going to be 100 cyclic versions, which will begin with HE and end with T. Okay? The, because you cycle them around, so 100 times you'll have word starting with HE and ending in T. Now, they're written in alphabetical order, which means probably all those words will be all bunched together, pretty much. So you'll end up with 100 T's at the end. So you don't bother writing T down 100 times, you just write 100 T. And that's why it's easy to compress. That's why it's easy to compress. It's almost magic. It is almost magic because, for instance, the first column there doesn't work in that if I just send you the first column, any message which has the same frequency of letters will have this identical first column. So in other words, you can't get the message back out from the first column, or indeed the second, or any of the columns, except by a piece of mathematical magic. You can always recover it from the last column entirely. And I wish I'd invented that. I didn't. But the bit of maths, the Burrows-Wheeler did it. But the bit of maths I did was related to Burrows-Wheeler transforms, and I'll tell you what I did. I put a certain semi-group spin on it, and what I did was relate it to what's called DeBruin words. And a DeBruin word is, here's an example. Oh, but you can't see it. Oh, here we go. That string of 8 symbols there, if you start from the beginning and write down all words of length 3, and then start from the next place, and continue on, and keep on going, what you get is all the words of length 3, without any repeats. I've done this wrong. I don't think I have. 1, 2, 3, 4, 5, 6. Oh, I have done it wrong. Too much of a hurry. 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1. Then after that comes 1, 1, 1, 1, 1, 1, and then 1, 1, 0. Yeah, in cyclic order you get those 8 words. That's called a DeBruin word. It's very nice, and it's used in, for instance, in the design of washing machine dials, because if you imagine those symbols now, the original word going around in a circle, and you have a dial with a window of length 3, as you click the dial around, you'll get all 8 possible settings without any repeats. And you can do this for, not just for n equals 3, but for any n, we can get a DeBruin word of length 2 to the n. And what I did was put a semi-group spin and found a connection between Burrows-Wheeler transforms and DeBruin words, in that I used what's called the generalized inverse Burrows-Wheeler transform, which is a mouthful, and show that can generate DeBruin words with additional properties, such as being first in its dictionary and so forth. So that was the basis of that particular paper. It's not typical of what I do, but it's an example where I've used the kind of algebra I do to do something almost applied, almost of some use. And I just want to finish with this picture. That's your cue. I'm coming up towards the end. I won't explain everything about this picture, but it's called a DeBruin graph, and it's very good for people who are drunk. because you imagine this is a town, and these are the houses in the town. And say you live in 1100, 1100, and you're wandering around. In the DeBruin graph, if you want to get home, you just say the name of your home and follow the arrows, and you always get to your home. For instance, if you're here, you just go one, whoops, get out of your way there, 1, 1, 0, 0, and here you are, you're home. And if you're here, I don't know where I am, but there goes the 1, there goes the 1, there goes 0, 0, and you're home. Isn't it wonderful? Even if you're already home and you're so drunk you don't know you're home, it will still work. Oh, let's see, 1, 1, oh, where am I? Oh, that's a 0 there, 0. Oh, it's there in the first place, that's good. So it's not clear what the connection with DeBruin Words is. It's to do with what's called the Euler paths of the underlying graph. And you can see I'm starting to having to talk about things that I can't really explain. So that's probably enough for tonight. Thank you, Kevin. So I'll hand over back to you. Thank you for coming.
Right. We have time for some questions, and people are busy getting the microphones to bring it to you. So do we have any questions, please?
We will be outside later, won't we? People can talk to us.
Oh, during the break. But we have a question anyway, so if somebody can get round to one of the back was first, I think, and then after that was somebody in the second, third row. No, fourth row.
Hello. You know about how you talk about the Burrows-Wheeler transform, like with banana, you either had two ends, B, A, A. Would you just write it out like that, or can that just be compressed further? Or is that the furthest you can go?
That's it. I mean, I didn't explain the idea entirely because you compress whole messages. So people would say, what happens to punctuation and space and things like that? You have to have special symbols for space, special symbols for punctuation. And also you need a special symbol to tell you where it starts, which you only use once, of course. And that's the saving grace. Because you might, if you think about it, think of that banana array. Any of those words would generate the same array. And of course, give you the same final column. So in some ways, it doesn't give you the banana back, it gives you all the cyclic versions of banana, which sounds annoying, but for a computer, that's not a problem. And if you have a symbol that tells you which one is the start, you'll ignore all the others and you'll be able to pick it out. So there's a bit more to it. And I think there's other clever wheezes they use to make it even shorter. But you see, in full generality, it doesn't do anything because you're replacing one string by another. So if you just start off with a truly random string, you'll get a truly random string back, and it won't be compressible. But you don't want to send truly random strings. You want to send, shopping messages and what you were doing last night and all that kind of stuff. And you want to babble, and you're going to repeat yourself all the time. And basically, this thing is saying, yeah, I know really what you're saying. You really only need this much. But making that idea concrete is what compression is all about. I mean, it's used on TV all the time. When you're looking at a broadcaster, all those pixels, they don't send all those pixels down the line every time, because all you need to do is send the difference between the picture you're looking at now and the picture you're going to look at in an instant. And if you're looking at a news presenter reading, there's hardly any difference. It's only when it changes shot to something completely different. You have to wake the system up and saying, oh no, there's going to be a big jump now. So you're really going to have to use all your power to get the next picture in. And then you can go to sleep again and just take differences and just send through that information, which allows you to keep reconstructing the picture completely. There's no loss of information in doing that. But you don't have to repeat yourself all the time, and like I'm doing, and like we all do. And the computer systems and the algorithms get around that and just send just enough information to say, look, I know what you're really saying. It's this, isn't it? Yeah, it's just what I said. Exactly. So that's what Burrows-Wheeler is doing, and that's what television broadcasting does all the time.
Right, I think we had a question from down here. No? You don't want to? No, you won't do that side. Okay, so there's now one up the back there.
Is it on? Yeah. Were you writing a new edition of your 2007 work? What would you be saying about the current state of the financial system?
I'd say you should have listened last time. Pretty much. No, I'm not a financial expert. I just mentioned it because I did write it before it happened and not after. So, yeah, I don't know anything more, probably less than a lot of people here. But yeah.
Right, do we have any more questions, quick questions before we go to TV? No? Okay then, so let's thank Peter again for his wonderful talk. And